Okay, welcome back everyone. In the previous session, we discussed about the first Erlang distribution and how the first Erlang distribution can be used. The equation can be used to solve the circuit switching based system. Okay, so issues. Moving on, we'll see the grade of service derivation of the queuing system. You know, the queuing system is a store and forward technique. Unlike the circuit switching system or a last call system, okay, any call which is arriving into the switch encounters a congestion will be put in a queue. Okay, in this case, in case of congestion, the calls or the information that's being transmitted won't be lost, and it will be delayed, but it won't be lost, and it will be put in the queue till the servers. Okay, servers are nothing but the outlets. Okay, that outlet that we have seen in the first Erlang distribution has been given a different name. In this case, it is called as the server. Okay, until the servers returns available, okay, for the incoming queued call to be allocated. Okay, the assumption in this derivation is by and large the same set of assumptions that we have seen in the okay, the first Erlang distribution. Pure on traffic, statistical equilibrium, full availability, the same thing as that of the last call system, and the only difference is that calls which encounter congestion enter a queue and are stored until a server becomes free. Unlike the circuit switching system, the calls which encounter a congestion, they won't be lost. They will be put in a queue until the server become free. Moving on, okay, there are two situations that can be used, to analyze the grade of service of a queuing system. Okay, the first situation is that, okay, the number of calls entering into the system, okay, which is less than that of the n, where n represents the number of servers or the trunks available. If the number of calls that are arriving into the system are less than is equal to the number of trunks available, then you can allocate all these n number of trunks to the x calls which are coming into the system. The problem arises only when the calls arriving into the system exceeds this capital N, where this N represents the number of servers or the number of outlets available. Okay, if the outlets available, the incoming calls can be assigned to the outlets. If the outlets or servers are not at all available and all of them are occupied, then it's a different situation. Okay, okay. In this case, the first situation that they are considering is when the number of calls are less than is equal to the number of servers available. Okay, in this case there is no queue. Okay, and behavior of the system is same as that of the last call system in the absence of congestion. Okay, as you know, the behavior of such a system in case of absence of congestion can be defined using the equation. So 1.7 that we have already seen from the mathematical model that we have seen, the behavior can be directly, okay, implemented as if, okay, is a lost call system. Okay, the next situation is if the number of calls coming into the system exceeds the number of servers available. Okay, if the number of calls, okay, coming into the system exceeds the number of calls available, if x greater than n, not is equal to, in this case, greater than n, okay, greater than n, only the problem arises. Only when this case the congestion arises and the calls are start getting accumulating in the queue. Okay, remember, in a queuing system, okay, the calls are not lost, but it is delayed, and then the calls are forwarded or connected to the outlets or the servers available after some duration of delay. The probability of, in this case, let's see the different notation that's being used. The probability of call arrival in a very short period of time, that is delta t, that is the probability with which a call arrive to a system, is given by P of A. You already seen this definition in the previous derivation, that is a mathematical model which is given by A times delta t over H. Okay, where h is the mean service time or the holding time of the call. Okay, next the probability with which, okay, probability of a transition from x minus 1 to x cos in a system is, in a system during delta t is given by, that is the call adding into the system. Okay, the call coming into the system is given by the definition. Okay, is given by this definition, p of x minus 1 times p of a, which is p of x minus 1 times what is p of a times delta t over h. Okay, where p of a represents the call arriving into the system. Okay, this is a state transition. The thing that we are defining over is a state transition of the system. Okay, where it is changing the status of x minus 1 call to the x call, whereas the probability with which a particular call might occur in that system is given by p of a. Okay, product of these two will give you a the probability with which a transition might occur. Okay, what's the transition probability of the transition of the system from x minus 1 to the x call, which is as good as the call being added to the system. Similarly, the probability with which call ends in a system is given by p of e, the notation, which is equal to capital N, which is the number of servers, delta t over h, where delta t represents the instant of time and h is the holding time. And the state, the transition probability of the system losing a call is given by p of x to x minus 1, which is nothing but p of x times, okay, p of e, which is given by, okay, p of k, okay, times n times delta t over h. The definition of p of e is not given. Okay, in this p of e is taken. Okay, whereas in this case p of x is taken as p of k in order to avoid the confusion with the actual p of x. Okay, moving on. Okay, p of k is taken. Fine. Let it be p of x itself. Okay, there is some changes in the notation. Okay, moving on from the statistical equilibrium assumption, we know that the transition probability, they are equal. Okay, there are no changes in the transition probability of a system, even if a call ends or even if a call arrives into the system. The the transition probability, a probability with which the transition of the calls takes place even when a call arrival in the system, even when a call ends in the system, remains the same. That's why we are equating both this transition probability, okay, and then moving with the derivation. And the definition of the probability with which the call ends, the transition probability with which call ends is given by p of x times n times delta t over h. Okay, so, and the call arriving into the system is p of x minus 1, okay, times p of x minus 1 times a times delta t over h. Okay, so moving on, this is the definition for the call ending in the system. This is the transition probability for the call arriving in the system. Okay, moving on, solving for p of x, you will get, okay, a capital A over capital N times p of x minus 1, which is equation 1.10. Okay, p of x, okay, the probability with which the call might occur in such a system is given by a power n over capital A over n times p of x minus 1. Okay, replacing x with n and generalizing this equation. Okay, let's say there are n number of in the present situation there are n number of calls available. Okay, so which is the beginning of a system. Okay, which is given by a power n over n factorial times p of 0 from equation 1.7. Okay, we in this case we are taking the equation 1.7. The definition of p of x given in the equation 1.7, which is a power x over f factorial times p of 0. Okay, which is the definition of, okay, equation 1.7, and we are using that equation to generalize the above equation, that is 1.10. Similarly, coming down, okay, if the p of x or p of n is getting one extra call to the system, you can modify the above equation in terms of 1.10, where you have a times a over n times p of x minus 1. Okay, instead of x minus 1, we are taking p of n. Okay, n plus 1 minus 1 becomes n. Okay, here in this case, from the, if you compare this equation with the equation 1.10, we are replacing x with n plus 1. If that's the case, what would be the x minus 1? It will be p of n only. From equation 1.7, we have the definition for p of n, and we are plugging that definition into the p of n plus 1, which results in an equation p a to the power of n plus 1 over n times n factorial times p of 0. Okay, see, from equation 1.7, you already know from the mathematical that p of x is equal to a power x over x factorial times p of 0. Instead of x, we are using capital N over here, okay, which is, okay, we are assuming to be the mathematical model. And moving on further, for p of n plus 1, we are using the definition of 1.10, okay, which results in a power a divided by n times p of n. Well, from the earlier definition of, okay, p of n, we have taken the definition of p of n and putting it in the equation of p of n plus 1, which results in this definition, which is a power n plus 1 whole, okay, divided by n times n factorial, times p of 0. Similarly, p of n plus 2 becomes a power n times p of n plus 1. Okay, n plus 2 minus 1 results in, okay, n plus 1. You know the definition of n plus 1, you plug in the definition of n plus 1, which is in the equation given over here. Okay, if you keep on plugging the value and adding one extra call to the system, you can simply generalize the above equation. Okay, in general, for a situation, the number of call exceeding the number of servers available can be given p of x is equal to a power x over n power x minus 1 times n factorial times p of 0. Here in this case, the whole n has been replaced with x. Okay, we are in this case, in the derivation, there is no need to be confused with x and n. It's being used interchangeably. Okay, the p of x in this case, it's a general, definition. P of x could be any number of calls, which could be greater than n or which could be less than n. Okay, that's why he is taking x in this case for the definition of p of x. Okay, that's why the whole term is like a power x divided by capital N to the power of small x minus capital N times n factorial times p of 0. As you can see, the value, the additional call that's being added, a numerical value that is there as the power of n, is been replaced with in terms of x minus n. It is being replaced with the term in terms of x minus n. As you can see, if this, okay, were to be some value x, okay, the 2 will be like x minus 1. If n plus 2 is equal to x, if you replace n plus 2 by x notation, 2 will be like, okay, x minus n. Okay, that's why they are replacing the numerical value, okay, that was available earlier in the generalized equation with x minus capital N. Okay, this whole term, term with p of 0 will give you, multiplying with p of 0 will give you the p of x. Similarly, moving on, further simplification will give you the probability with which the call might occur in a system. Okay, when the number of call exceeds the servers available when the calls are in queue is given by n to the power of capital N whole divided by n factorial times a power n to the whole power of x times p of 0. This equation is 1.11. You know that now we have got the definition of p of x. Okay, if there is a case when the call exceeds the number of trunks available. Well, let's take the summation of p of x for this queuing system. Let's take the summation of p of x for this queuing system for the interval 0 to infinity. Let us consider the queue we are assuming. Okay, it's an ideal queue where it can support infinite number of calls to be buffered. Okay, in this case, the queue we are assuming is a queue which can hold infinite number of calls. Okay, in case of congestion. Okay, the summation of this p of x which defines the probability with which call might occur in queuing system, is taken over a interval of 0 to infinity, and the whole sum is equal to 1. You know this theory. Okay. Now moving on, the same summation can be split into two intervals. Okay, the one interval, okay, is the condition where the number of calls are less than the server. That is, the number of calls arriving into the system are in the interval 0 to n minus 1. Okay, you can support, okay, the number of calls in a system, okay, without congestion, as long as number of call coming into the system are in the interval 0 to n minus 1. That means you can support, okay, all the way from 0 to call to the n minus 1's call in the system, because you have a number of servers. Well, the p of x in this case, the behavior can be defined using, okay, the same as that of the last call system that we already seen. Plus the next term represent the behavior of the system when the call exceeds the call encounters the congestion and they start buffering in the queue. Okay, when the number of call exceeds the number of server, the call the behavior of the system is defined over this interval. Okay, where k is okay, is given by x minus n. That means, you know, capital N represents the number of servers available, x represents the number of calls in the system, where k represents the difference between x minus capital N, where x is the number of calls coming into the system, where n is the number of calls that's already been serviced. The remaining difference of these two will give you the remaining calls that is available in the buffer. That's why the k is going to give you the picture or number of calls that are buffered. Okay, that's why k is given by x minus n. Similarly, x is nothing but k plus. The total call at a system is the number of call in the buffer and the plus the number of calls that's being serviced. Okay, please make a note of this. K is equal to x minus n, or x is equal to k plus n. K is the number of calls available in the buffer plus n. Total calls is given by x. Okay, the summation of this term is this p of x. The second term is the definition for the behavior of the system when the system encounters the congestion. Okay, moving on, you can expand the definition of p of x for these two situations. You know from the earlier definition, the first interval for the in the system, the calls are less than is equal to the number of servers available. It is same that of the last call system, and we give the definition of a power x over x factorial times p of 0. That is same as that of the equation 1.7 that we have seen. Well, for this case, okay, we're going to take the definition of the situation if the call exceeds the number of servers available. That you already seen the definition of for such a situation. The probability with which call might occur in a system in such a situation is given by the equation 1.11. That's why we are plugging in that definition of p of x in the interval k is equal to 0 to infinity. It's a condition where the call exceeds the number of servers available and they are start buffering in the system. Let this equation be 1.12. Okay, moving on. Okay, solving for p of 0, you'll get 1 over p of 0 is equal to, the first term is like the summation of a power x over x factorial between the interval 0 to n minus 1, which is a behavior of the last call system, plus, okay, the summation of n to the power capital N whole divided by n factorial times a power n to whole to the power of k plus n. You know the definition of x is given over here. X is equal to k plus n. I am replacing x with k plus n. Okay, moving on with the simplification. Okay, within the summation, I only keep the dependent factor, which is a power n whole to the power of k, and I am going to take out, okay, the independent factor, which is a power n whole to the power of n out of the summation. Okay, now the n power capital N cancels out, and which results in this term. Okay, moving further, we do the simplification. Okay, the first term, okay, which is s equals 0 to n minus 1 interval. In this interval, we are adding a power x over x factorial, plus the second term is like a power n over n factorial times the summation of a power n over a over n all to the power of k, and summation of this term over the interval k is equal to 0 to infinity. Now we know from the you know from your PUC, you know that when the the term a over n is less than is equal to 1, as it is a fraction, even if you take and do some calculation, it always this the value that you get when you divide a by n is always less than is equal to 1. If such a term, okay, to power of k, it's being summed over an interval 0 to infinity, you can always substitute such a, okay, summation with this definition. Okay, you might have know this identity from your PU experience. This old term, this old summation can be replaced, okay, 1 minus a over n to the power of minus 1, only if a power n less than is equal to 1. Okay, so that's why moving on further, we're going to replace this summation with this, as we have a power n to be less than or is equal to 1. Okay, moving on, for the same equation, p 1 over p of 0, the first term remains as it is. The second term, a power n over n factorial times 1 minus a over n whole to the power of minus 1. For the simplification, we'll get you this equation. Okay, the second term has been moved to the as the first term, which says a power n over n factorial. The first term simplification has been done over here, plus the summation of a power x over x factorial between the interval 0 to n minus 1. This is the equation 1.13, and the above equation is called as the second along distribution. The above equation is called as the second along distribution. I don't think the detailed derivation is not been explained in the material that I've shared. Please make a note of this. I will be uploading the same video in the YouTube. Make sure to go and follow it, look at as and when you have any doubts. And this derivation you I guess I've already given as a assignment. This is the detailed derivation. This is one of the important topic to be discussed. If at all they are asking the examination, they are definitely going to ask for 8 to 10 marks. Okay, this is one of the important question. Please make a note of it. This is all about the second along distribution, and this is what we need to be deriving, what you need to be deriving for the second along distribution. There are two more topics or two more derivation associated with the queuing system. One is the probability of delay and finite queue capacity, which is there in the material. Please go through it. By and large, it says the same kind of derivation of a second along distribution, which I'm going to leave it as an exercise to you. Okay, this is another important topic that might be there for your examination. This is one of the topics that might be asked in the examination. Next, moving on, we'll see the classification of switching network. Okay, the classification of switching node is based on the inlet and outlets of a switch available. Okay, classification of switching network can be done based on the number of nodes, inlets and outlets available. You can have a single stage switching network, you can have a two-stage switching network, you can have a three-stage switching network, and you can have a four-stage switching network. What is the single stage, two-stage, three-stage, four-stage switching network is what the discussion that we will be doing in this part of the module, in this remaining part of the module, and along with the grading technique is what we will be discussing in the further, okay, topics of a module 3. Okay, let's see what's the single stage switching network. Consider a simple switch. A simple switch, it's a matrix switch in telecommunication system where it connects some n number of calls to the n number of connection to the m number of outgoing connection. If ABC in this case, it's a simple matrix switch. Okay, if ABC are the inlets, the ABC which are connected vertically are the outlets. Any call that want to be connected to any one of the outgoing call can simply connect it by activating the relay. If I am to connect the inlet A to outlet B to make a connection, I simply excite the excite the relay 2 in the first row, which makes a connection between the horizontal and the vertical line. Horizontal and the vertical line. Symbolically, such a matrix switch is represented by symbols which as shown here. So symbolic representation, it's a matrix form of representing a switch. Okay, you have M is equal to N outlets. In this case, it's a 3 cross 3 matrix switch. Okay, the total number of cross points in this case is N squared. N squared. The cross points are nothing but the number of relays that's being used to connect the vertical and horizontal lines. Okay, the intersection of vertical and horizontal lines, they are called as the cross points, and they use relay at these cross points, okay, to make or break the connection. Moving on, the cost of these such a matrix, it depends on the implementation or use of how many relays that being implemented. In this case, the number of the relays that being used to make or break the connection in such a switch is N squared, which is being squared. Okay, which being squared. If there are ever increasing number of N, the it also increases the cost in, okay, which is a square of the number of inlets and outlets available. Okay, as you can see, thus the cost increases at the square of the size of the switch. Okay, if there is an increase, because the relay is made up of copper. The copper, it's a very expensive material. Okay, if you are using more number of uh, you know more number of wait for a minute. Wait. Okay, if you have more number of inlets and outlets, the cost increases square of that of the inlets and outlet. Okay, however, efficiency of such a system decreases, because given a point of time, if calls are coming randomly into the switch, you won't be using all the relays, which obviously going to reduce the efficiency of the system. If there is, it is therefore uneconomical and to use a single stage network for the large number of inlets. As you know, if the number of inlets or outlets outlets, as you know, they are equal in any matrix kind of a switch. If they are increasing, the cost of such implementing such a system also increases, which also results in reduced performance, and also it is uneconomical. Reduced performance because the cost with which we are implementing such a system is not yielding enough productivity. It's because most of the time, not all the relays that being used are not being the relay that being used to implement such a system is not being used to engage a call. Okay, if you are to increase the number of inlets outlet for such a system, okay, you need to be making a network like structure. That means you need to be make an interconnection of these switches to form a network like structure of several stages of switches to make the system more efficient. What is trying to tell is that if the number of inlets of a system or number of outlets of a system increases, okay, if it is the if you are to implement a switch with large number of inlets and outlets, in uneconomical to implement as the single switch. It's better to use the combination of small switches to construct a network of switches, okay, to support more number of calls, okay, to support more number of calls, which is more economical and more efficient compared to implementing, okay, a single switch which can support thousands of calls. Okay, so moving on. Okay, this is an example of two-stage switching network. If this n inlets and n outlets of a switch were to be like in terms of thousands, it is okay, economical to take a small switches and connect them like a network like this, to implement more efficient and reliable and economical, as a more reliable economical switch. As I told you, if I were to implement this whole system as a single switch, in the economic point of view, it is not feasible. To make it economical and more efficient, you take small switches and connect them as a network like this, to make the connection between, okay, more number of calls. If calls were to be, or inlets and outlets of a switch were to be in terms of thousands or hundreds. Similarly, it's a three-stage network. This is the extension of two-stage network. Instead of three stages, you have, okay, three stages. Okay, in this part of the module, we'll be discussing about how to design this two-stage and three-stage network, and also the how to derive the grade of service of such a switching network, what we'll be discussing in the classes to come. Okay, next we'll see the grading. Okay, grading, fine. With this, I am winding up the class session for today. We'll see the grading in the next class.
How many loop control variables do I need now? I just want everyone.
Okay, we'll meet in the next session. Okay, we'll end the session for the day. We'll meet in the next session. We'll let you know about the next session.